Hi everyone, Mrs. Pasega here, and today we're learning about defining systems and using them to write equations about energy. So let's say we start with an easy one. A car rolls down a hill. It starts from rest at point A and is moving at point B. First thing I'm going to do is draw a picture. This will generally be done for you ahead of time. At point A, the car is above the ground, so I would write that its height is greater than 0 and its velocity is 0 because the problem states it's at rest. I'm going to draw my reference line here, and the reference line defines where we're going to call 0, or the ground, on Earth. Now we're going to label the system. The car is in the system, but so is the Earth. The Earth has to be in the system, or else you don't have gravitational potential energy. At A, I have gravitational potential energy because at A, it's above reference. There's no kinetic because it's not moving, and there's no spring because it's not touching any springs. Now let's take a look at B. At the bottom of the hill, that's where our reference line is. So I would write that YB, the height at point B, is 0. But the velocity is greater than 0. It's definitely moving at the bottom of the hill. So I would draw kinetic energy equal to potential energy with no gravity and no spring energy at the bottom. Writing a quantitative equation for the system then would be that potential energy at point A is equal to the kinetic energy at point B. Though, if you really wanted to, you could also substitute in our mgh at height A is equal to 1/2 mv squared at point B. All right, next. What if I accidentally forgot the Earth? Does this still work? The problem setup is going to be the same as before. We're going to have our car A at the top of the hill. It's going to be above the ground, all that good stuff. But the difference is, if we forget the Earth as our system and we only include the car, well, that kind of changes our energies here. Let's say we define our system as just the car. At point A then, I couldn't give it any gravitational potential energy. It would look like I have 0 energy to start, turning into kinetic energy at the bottom. Well, that's no good. That means we have misdefined our system. You've defined it incorrectly. And if we've defined our system incorrectly, it looks like there's 0 energy to start and kinetic energy at the end. There must have been some sort of external work done by an unknown external force. But guys, we know what that external force was. That was gravity. It was just we forgot to define the Earth in our system. So let's try it again. All right, in this problem, I've got a ball launched up into the air. It's at rest inside a spring-loaded launcher at point A. It's moving and above the ground at point B, something like this. So first, let's define our reference line as being exactly at point A. That allows us to have 0 gravitational potential energy to start. We would say that the height of A above the ground is 0. And let's say that the spring is part of our system. So this would be the spring, ball, earth system. All 3 of those interact with each other. At point A, there would be no height, so no gravitational potential. It says it's at rest, so there's no kinetic energy. But there's spring potential energy. PES, or spring potential energy, because of the compressed spring. Now, someone was asking, do I just pick random numbers here? Yeah, I'm picking 3 bars randomly because this is just a representation. It's to help visualize. At point B, I know it's above the ground, so the height is above 0, and it's moving. Okay? So that means there's some kinetic and there's some potential. But what I'm picking for these numbers here doesn't super matter as long as it adds up to 3. So I randomly picked 2 for the kinetic energy and 1 for the gravitational potential energy. And I could write this correctly as spring potential energy at point A turns into kinetic energy plus gravitational potential energy at point B. Ta-da! But what if, like before, I accidentally left an object out of my system? So it's still a spring at A, still moving and above the ground at B. Same reference line. If I accidentally forget to include the spring, that means there's no energy to start, no kinetic, no potential, no spring, because we've left the spring out of the system. So this looks like kinetic and potential energy just came out of nowhere. It looks like 0 energy turns into 3 units of energy. We would call this work done by an external force. What was the external force that caused it to move? Oh, it was the spring because we misdefined this system. One more incorrect one and then we'll sum this up. Let's say we forgot the Earth again. If we forget the Earth, we can't have gravitational potential energy. So I'd still have spring potential energy at A. We'd have to define the spring as part of the system. I'm keeping with 3 bars just to be consistent with the previous examples. If we call this the ball spring system, it still has spring potential energy, but us neglecting to include the Earth means there's no gravitational potential energy at B. And it looks like the spring lost energy. Where did that quote-unquote loss come from? Well, there must have been work done by an external force that slows the ball down. And what force slowed the ball down? Gravity, because we forgot the Earth. So let's sum this up. The law of conservation of energy says that the total amount of energy in a closed system is conserved. In a closed system, the objects only interact with each other and no other items. So let's say I take a block that's moving at point A that hits a rough surface and is stationary at B. It has kinetic energy to start, but it's not above the ground and it's not touching a spring. I'm going to call this the block Earth ground system because A is going to interact with the ground. And at B, there's no kinetic, not above the ground, not touching a spring. So where did this energy go to? Guys, that kinetic energy turned into heat. EINT is thermal energy. The kinetic energy turned into heat, the internal energy of those particles vibrating around. So if I had to sum this up for you, it goes something like this. First off, identify 2 points or more at which you can identify the energies. Sometimes this will be done for you. Draw a reference line at the very lowest point of motion in the system. This allows everything to be positive, and maybe the energy is 0 in some places. Then, define the system of all the objects that interact with each other. Usually, that's going to be the Earth plus some moving object, and sometimes a spring. Finally, that means the energy total is going to be equal at any time. So maybe I would write this as energy before is equal to energy after. And if you've misidentified something and they're not equal, that means some additional force has done work that we haven't thought of yet. All right, guys, so I want us to go try this on our own. In homework 4.1, please try problems 6, 7, and 8. And remember to do all the steps. Don't leave out the reference line. Don't leave out the system. And make sure that when you're writing your energy equation, that your energy before at point A is equal to your energy after. If you end up at the end of a problem and it doesn't look like they're equal, that means external forces did work. All right, guys, best of luck.